Hello, my name is Chun Chan, and I am an associate professor at Deakin University. In this tutorial, I will talk about deep learning and what might go beyond the current paradigm. The reason for this tutorial is that I think the field of deep learning has reached its maturity with a huge ecosystem to develop and deploy in the real world. When a field reaches this point, it is the right time to think about what might be the next. Let us start by reviewing a very short but exciting period of the past 8 years. It started with the deciding moment when a deep neural network called AlexNet won the ImageNet challenge. The ImageNet dataset was considered to be one of the largest of the time. It has 1 million images and 1,000 categories. Before AlexNet, the standard of the days was having a powerful feature extractor designed by hand, followed by a clusterings and an support vector machine classifier. AlexNet changed all that. Now the features are learned together with the classifiers. We have image in, category out. Simple as that. Only 4 years after the AlexNet, there was another deciding moment when AlphaGo from DeepMind defeated Lee Sedol, one of the best human players of our time. Unlike the Go software that came before it, AlphaGo learns everything from the ground up. The winning was a defining moment because Go was considered to be too hard for computer, and people expected many decades before the machine can defeat human. In the same years, I gave a tutorials in deep learning in Australia, in Canberra, with the focus of non-cognitive domains. At that time, deep learning was very successful on domains where humans have no difficulties, such as image and speech recognitions. Since then, the field has matured very quickly beyond that point. And today, we have deep learning in all fields where we have a lot of data. As a result, the deep learning pioneers, Jeff Hinton, Joshua Bengio, and Jan LeCun, won the Turing Award in 2018. Just 2 years from that point, and in 2020, OpenAI released GPT-3, a very powerful natural language model that can do very expensive things like generating story that reads like human or a piece of code. GPT-3 is a very huge model with 175 billion parameters. This is so impressive to the point that Jeff Hinton speculated that we may just scale neural model to do almost anything we could with just 1.4 billion parameters. Whether that idea of scaling is the way to go, we don't know yet. But chances are we need both scaling and new way of advancing deep learning. Given the impressive track record of deep learning, why are we still concerned about deep learning? Why we are not just considering deep learning as standard tools and we use just without thinking? Right? There's two main reasons for that. One is theoretical, another one is practical. From the theoretical side, there are important aspects of a machine learning paradigms that need to satisfy to make an impact. One is expressiveness. The second is the learnability, and the third one is generalizability. Neural nets are known to be expressive because we can find any function and we can approximate that function with a neural networks. But of course, approximation is not enough because if we can't find a way to learn it, it's not useful. Fortunately, neural networks are very easy to train because the current advances in stochastic optimizations and neural architecture design that makes the learning easy. And in fact, most of the time, we don't need to worry about learning anymore because everything is like standard setup with the current programming frameworks. And the third point is generalizabilities. Neural networks are known to generate well, even if we have the over parameterizations. However, neural networks are still suffering from adversarial examples, and that's still we still do not know why and how to avoid that yet, even though there are a lot of progress in the last few years. On the practical side, deep learning appears to be a general purpose technology. It means that it can be applied to almost all the domain where we have data. The second point is that deep learning is currently the very competitive algorithms or methodologies, because it's very hard to find real competitors when we have a lot of data. And the third point is that deep learning is scalable. In most of the time, the complexity of deep learning algorithms is linearly scaled with the data size, and it enables the deploy deep learning in the real world. However, for someone new to deep learning, the fields of deep learning look very daunting. There are tens of newspaper published every day, and new ideas appearing every single week. And every few years, we have a major breakthrough that totally change the way people approach the problems. And of course, that is one of the main reasons why we have this tutorial where we would like to guide you through the major ideas that actually works. Now we have literally hundreds of models. They are very well known with model with theoretical properties, starting from the very first version called perceptrons, then advanced to the multi-layer perceptrons. And then as of today, we have CNNs, INNs, LSTM, Hopfield networks, and some well studied but less popular today, like boson machines. In 2006, when the current deep learning wave was started, we have the plenty of options, like restricted boson machines, denoising autoencoders, deep belief networks, and other things. But more recently, we have GIUs, Turing machine, neural Turing machine, capsule networks, and attention networks for us to choose from. Given that we have hundreds of models, it's a good idea to ask what are the common design goals among those models. I list some of them. It's not a complete list, but some of the goals that I think that important when we design a neural networks. One of the trend that we've been seeing in the last few years, in fact, in the last few decades, it's the uniformities. It means that we can build a very complex model using the same building blocks repeated over and over. Another feature is reusability. It means that we can train a small model for a particular task and can reuse the same model for a bigger and complex task. Very importantly, for a model to be effective in the real world, it have to have the capability to capture the long-term dependencies both in time and space. It also must be reliable, less sensitive to variation in the data. Like for example, in image, a good model had to be insensitive to against rotation, shifting, scaling, and some white noise. In other words, it have to be invariant against these variations. The list can be long and go on, but more successful models these days tend to meet more goals than the other that came before it. For the rest tutorial, I will cover the following topics, and they are organized in two parts. The first part is called Deep Learning 1 version 1. It covers major ideas that works in practice up to now. However, those ideas are still limited with the current offerings. And second part would cover the other ideas that are not in the mainstream today, but may have the potential to remove the fundamental limitations of the current models. Since there are many concurrent ideas being developed and practiced by pioneers, it's hard to pick all of those ideas. And in the part two, I only consider a few major ideas that I think that may be important for the next phase of deep learning. For now, let's start with the classics model first. So deep learning starts with a very simple idea that we have a neuron, which is a computational unit that takes a couple of inputs and then compute the weighted sum of those inputs, and then passing the idea through a nonlinear transformations. Very simple. The good thing about this is that we can replicate the unit uh, multiple times into the building block. And then we can stack those building blocks together to create a very deep model. The good thing about stacking the building block is that theoretically we know that the deep models are more powerful than the shallow one given the same number of parameters. However, training a deep model is very difficult. So that the first generation of deep neural networks actually have not very deep. They have only one hidden layers. One of the reasons for that is there's nonlinearities in the transformations. And if you stack multiple nonlinearities, then the two problems might happen. One is that the gradient that we compute may be vanishing. It means that there's no communication between the inputs and outputs. Or the gradient can be exploding. It means that it's super sensitive to any small change in the inputs. Both is the case, it stopped the learning from happenings, and therefore the network is not learned as expected. The main idea that have changed that problem is have to solve that problem is called skip connections. And very generic ideas, and it have a long history starting from the early days of LSTM in 1997, roughly 23 years ago. The basic idea that we can create a shortcut in the computational graph so that the flow information can have another path rather than just going to the sequence of nonlinear transformations. And in that way, we pass certain non-linearities to the output. We maintain certain linearities from the input to the output. The idea is very simple, but it allows us to having non-vanishing gradients. As a result, we can build 100 layers, not just one like before. We can build 100 layers and still be able to train the models. This is a simple idea, but it actually changed the field a lot. And now it is a standard component in all the modern high-performing models like LSTM, GIU, ResNet, or Transformer. And here example of how skip connection is being used in ResNet. It looks complex, but the idea is quite simple. That we go through the two channels to pass information. One is the sequence of nonlinearities. Another channel is just copying. And then we add them up. Very simple tricks, and that works extremely well. The second important architectures is recurrent model. It is important because theoretically, we can represent a Turing machine using neural networks, recurrent neural networks. However, learning recurrent neural network is not easy. The problem is same as before. We have with many nonlinearities, we have either gradient vanishing or gradient exploding. The ideas was using skip connection, and we have the LSTM and GIU. And given that ideas, now we have INN just run in all complex and measures application in video processing, speech recognition, or language processing. With that, now we have we can do a lot of things like say sequence classifications, or image captioning, or sentence classifications, machine translation, or labeling of sequence. You can name it. The third important class of model is CNN. It's based on the concept of convolutions, standard concept in signal processing. The idea is that we can pass the signal to a kernel so that the outcome of that have certain properties that we want. The convolution neural network change that fundamentally by learning the kernel itself rather than designing by hand. It is simple idea so that it can be applied to a sequence, an image, or tensor, or video. CNN can be applicable to whenever we have the data that arrange in a certain way, and we have the data that have repeated patterns in image, speech, language, or even our own DNA. And it can be applied to 1D, 2D, 3, or 4D, and it can be combined with recurrent networks to make the models flexible and complex. A typical convolutional networks have multiple layers. It starts with the input, which may have one or more channels, and through convolution, it created other set of channels of the same size, and then going to poolings to reduce the size, and that convolution and pooling pattern could be repeated multiple times until in the last stage we flatten out the convolution map and connect to the few fully connected networks before doing classifications. So far I have reviewed the feed-forward networks, recurrent networks, and convolutional networks. Recently, we have seen another idea which show the power in many rich domains, and that idea is attentions. The attention is different from the other three ideas is because of the feed-forward networks makes assumption that the data are ordered in certain way into the vector. Recurrent networks make the assumption that the data are ordered sequentially from left to right. And the convolution networks assume that the data are arranged in spatially in certain way. But attention make no such assumption. It takes the input as a set, and the set is unordered, and it output another set or another item or set depending on how we implemented it. The idea have the gains important in recent years. It's basically compute the normalization across the element in the set, and then extract the wasted sum information from the set. It's a very simple idea, but it works very well. And it also reflects the way that human possess the real world, because there are irrelevant information in the world. And at the single time, we only pay attention to one of the piece, one of the signals that are relevant to us. So attention is one of the mechanisms that allow us to achieve that the same goal. Computationally, that it have another properties, very important properties. It created a shortcut between any a input element to any output elements. They're only single path, single step from input to output, regardless of the length. Of course, we have to pay the price for increasing computations, but the fact that we can make the long-range dependency arbitrarily across input and output, that's a very powerful idea, and that um, defied the success of many neural network architectures. The attention can be soft or hard. If attention is soft, normally it computes through softmax, and they are differentiables. But attention can be hard by picking discrete element at a time. So because of hard attention, sometimes we need to change the way to handle the hard attention. And one of the more popular ways to use reinforcement learning um, to take care of the discrete operations. Now we have covered four ideas: feed-forward network, recurrent networks, convolution networks, and attention mechanisms. And those make the assumption that the networks um, can be defined. And the next question is, how do we learn the weight of those networks? How do we learn the parameter of those networks? Right? The standard way to learn the parameter is to optimize the network predictions in some training data, right? By minimizing some errors or maximizing some log likelihoods or minimizing cross entropies. But it could be very slow because we have to collect a lot of training data, pushing through the expensive optimization algorithms to get one set of weight, and it doesn't change after that. Right? Of course, we can change that, but updating the model is expensive, right? And it's not flexible enough. The question is that the only way to estimate parameters? Remember that our brain have roughly 100 trillion synapses, and we live only about 1 billion seconds. And it seems like we don't have enough time to learn to update those 100 trillion synapses. There must be an alternative way to estimate the weight. One of the interesting idea that's been there for 30 years, or even more than that, is called fast weight. The idea is that the weight itself do not need to train sequentially and slowly. It can be just updated and computed from the data itself. So the weight is data independence. So it can be implemented as another using another network called controller networks. The idea is that we have the main networks with the parameters, and the controller networks take the input of the data and produce the outputs as a weight for the main networks. So that idea has been there for a while, and recently it being realized in the recurrent neural network through the model called hypernetworks. And very interesting because it opened up the chance for very dynamic data dependent weights. So that if things change and the model can adapt like in real time. Unlike the classic setting where we only update the model from time to time, like slowly, periodically from time to time. Right, now we have the model weight, and we make the assumption the model can be designed. However, is that the optimal way? What is the optimal way to design the models? We don't know yet, even though we have at least few basic mechanisms like feed forward with stackings, recurrence, convolutions, and attentions. But how do we combine those things together when we face a very complex problem that no single model can have? And it poses the question of, can we learn to design the model itself through the data? Rather than design by hand, can we build a machinery that's learned to design a model, right? It's kind of hyper idea, similar way to the hyper networks where we learn a model to generate the weight. Now we learn a model to generate the architecture itself. And that has been there for few years, and the activity is quite um, popular these days, right? But the problem is that the space of all possible model is very, very large. It's unlike the space of weight, which have the fixed dimensions. The space of all possible models is discrete and very, very large, right? And searching naively have no chance of success. So one of the recognition is that the model itself, even though it could be complex, but it can be described as strings. So each of the element in the string describes one component, right? So the idea that if we can learn a way to generate such kind of strings, we have a way to generate a model, right? Its idea is quite simple, but the implementation of the idea is not easy because the space of string again is big. So the popular way these days is to use um, reinforcement learning to sequentially generate one option at a time. And then it could be followed by optimization, discrete optimizations. But again, this is expensive operation because we have to generate models, test model in the training data and testing data, and keep generating model again. All right, so far I have covered the multiple ideas that have been popular and working, um, and that all of those ideas came before and roughly before 2016. By 2017, there was another breakthrough happens, and the breakthrough was known as transformer, designing by Google's. Transformer itself is not a new idea because it's based on the old ideas like attentions, position codings that came before, way before transformer. However, what Google did was that it got all element right. Since then, transformer has found its place in many modern applications, and more often than not, with enough data, we can create a transformer-based model that wins over the existing models. Now let's go into it. So before we go into the detail of the model design of transformer, let's start with some reason why we need the kind of new architecture at all, given that we already have feed-forward network, recurrent networks, and convolutional networks. And those combinations can do most of the work we need. So one of the main reason is that INN we known to be theoretical powerful, but because it's sequential, so it's quite slow to learn and to run in practice. Right? And also normally it has the limited memories because in theory it can remember very long sequences, but in practice the memory is quite short, only a few steps. One of the ideas is to augment the an external module to the INNs, but the net effect that the entire system is even slower. CNN, on the other hand, is a kind of feed-forward networks, and therefore it can be parallelized. But theoretically, it's not very strong because it doesn't have the good mechanism to maintain the long-term dependency explicitly and maintain the information that we can recall at any time we like. So before 2017, most architecture are a mixture of either feed-forward network, recurrent networks, or CNN. The problem is that it makes the model designing a bit complex because there are non-uniformities between those elements. And it's not easy to scale to a large number of different tasks. And every single team had to think very hard about how to design a model for a task. Right? So we need something scalable, theoretical, powerful, and easy to use and design. So before we go into the detail of the transformer, let us start with the important ideas that is not popular this day, but it had all the important elements that go before the transformer. The idea is known in 2006, 2015 as in memory networks. The memory network is a recurrent neural networks that is augmented by a external memory. So the memory is simply a matrix where each columns represent a data input. Right? The recurrent controller make sequential query to the memory, reading from there, and combines those readings in a certain way, and then finally compute the answer. This look like a simple idea, but it have important elements. One is that memory readings. So to read the memory, controller have to issue a thing called query, right? And the query, and then given the query, we compute something from the memory called key to match with the query. So whenever the matching is found, we attract the memory slot with the where the matching happens. Even though that's a simple idea, but implementation is not easy because the matching could be discrete, right? So to enable the continuous matching, people use the concept of attentions. It means that we consider how much the degree of matching between the query and the key, and then use the degree of matching to compute a weight. So each of the memory slot could be retrieved. From that match, from read that gives us a reading of the memory, where the output is not a single memory slot, but the wasted sum of all the memory slots. That's simple ideas, and but it have very interesting theoretical properties. For one is that it gives us the constant path length from the input to outputs. Unlike the very deep feed-forward networks where the input only touch the outputs through multiple intermediate layers, with this kind of memory architecture, the input is almost directly connected to the output. And the path length from any input to the output is constant. And from the model point of views, this one is a INN with a shared input set. Unlike the standard INN where every single input step could be different. And this one, every single step on INN, the input set is the same. The only difference is that we have the attention mechanism to pick which of the element of the set to be read into the INN. Now we have the three idea that memory, state, values, key, and queries. The transformer actually is the way to make all of the operation in parallel. So transformer works like this. It assumes a sequence of input. For now, we assume that the sequence of tokens, discrete tokens. So transformer actually didn't do sequential processings. Instead, it encode the positions of the token into the together with the token embedding to make it the input feature for each tokens. And then for each tokens, it issues a query to all other tokens based on the similarity between the key and queries, just like the way that we did for the memory networks. Then, based on the reading, could be one or multiple reading steps, the values of all other tokens or the feature of other all tokens are pulled together combined with the current tokens, to form a new feature representation of the current tokens. And of course, transformers doesn't just do that. It have many other elements that make it makes the idea works. So we have multiple reading heads, and um, it have the feed-forward network to transform the readings, and it have the skip connections that allow the information to pass in the multiple parallel way. And then you have the layer normalizations, which known to be important for this kind of complex architectures. So as a result of each operation, all of the tokens representation are updated at the same time. The idea of this called cell attention is because attention is because of the key and the query and the values come from the same source, which all come from the representations of the token themselves. So optionally, we have that will give us the way to encode the data. Optionally, we can create a decoder so that each time step we generate one output by pulling the information from the previous steps and the information from all the input in the encoder. The question is that why transformer works, right? It has been practically has been shown to work extremely well on many tasks. The beauty of that is that the architecture is very uniform. We apply the same computational unit to all elements in the data, and regardless of data type, we can make use of the same kind of operations, right? So many tasks can be reformulated in this way, and making the transformers a kind of like a universal representation learning method. The question is that what makes the transformer so effective? Is there any theoretical reason behind it? So this year there's been a new breakthrough. The works by Bram Sawyers saw the links between transformers and the classic model known as the Hopfield networks. For those who don't know, Hopfield network is a classic model introduced in 1982, and is special kind of the recurrent neural networks with the binary states. So the special thing about Hopfield network is that each of the units flip its state depending on the incoming wasted state from the neighbor. So put in the modern term, it's like state refinements, right? Very, very similar to what we have in transformer. Like in transformer, we have a token that refine the feature of itself. And in the Hopfield networks, you have the unit that refine its own state based on the information of coming from the other states, right? So there's certain similarity between the two formulations, but that's not enough to draw the direct link between the two. So what is new here is that Ramshaw and colleagues found that transformer is actually equivalent to a special kind of Hopfield networks. And more importantly, the state refinement operation in transformer actually minimize the specific energy functions. This is very interesting links. And that might offer a new insight to explain why transformer is so effective and so universal for both representation learning and reasoning. We'll cover the reasoning part in the second part of the tutorial. But for now, um, we can just happily say that the transformer is a kind of modern hardware networks and transformer operations, cell tension operations, actually minimizing certain energies functions. And that's very exciting. Now we have covered the memory networks and transformer. And it's a good idea to draw the connection between the two models. So as I mentioned, there is certain similarity between the two because both use the concepts like memory, attention, and iterative state refinements. The main difference is that, however, is that transformer consider memory as a multiple state to update in parallel using cell tensions. Memory, on the other hand, doesn't update the fixed memory. It only updates the state of the controller, which equivalent to the one node in the one token in the transformer, right? And that make the memory network a bit of limited because if the input state is not defined and we don't know if the input states are correlated, then the memory network itself doesn't make use of that inductive bias to improve itself. Now we have the transformer. However, transformer is still a kind of feed-forward networks in the same way that CNN is a feed-forward networks. And because the feed-forward network doesn't have a way to carry the recurrent property, which give is the power of a Turing machine. So following the publication of transformer, there was another works from DeepMind that extended the transformer to be recurrent. So the idea that each of the tokens itself is the recurrent neural networks, and it have the power to update itself multiple times, repeatedly, and independently. Right? The number of steps each of token update itself could be defined, could be determined automatically depending on the need of of updating. And another key idea that all the operations across a step of update and across a layer of transformer itself share parameters that make the transformer a recurrent neural networks. And 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 then it have the very nice property of the Turing machine that we might expect um, a powerful model to achieve. However, with these recurrent steps, multiple recurrent steps, we add multiple, we multiply the complexities multiple times. And as a result, although the universal transformer is theoretical powerful, in the practice, it's quite expensive to apply. But let's see how it turn out in the future when we have the faster algorithm or we have faster computations. Right. So from now, probably you are aware that transformer is powerful, but also quite expensive. This is because every token have to connect to all other tokens. And the result of that, the complexity is quadratic in number of tokens. Imagine we have the documents with 100,000 tokens. Then the complexity of updating the model is refining the state is too expensive to do in practice. Right? So as a result, in the last few years, only 3 years, there has been a couple of dozen of models try to improve the speed of the transformer. Right now, we have certain versions that are linear in number of tokens or sublinear or subquadratics. There are many ideas behind that. One of the main ideas that recognizing that the attention matrix, cell attention matrix is quadratics, and it could be in low rank. And because it's low rank, we could find a way to factorize that interaction into in smart way, right? So factorization could be done in multiple ways. One is using explicit low-rank decomposition. Another one is just try to use um, some virtual nodes so that token do not need to connect directly to each other, but through the intermediate tokens. And that gives a way to implicit factorizations. So I don't have enough time to go into detail of all of the techniques that are being introduced in the last 3 years. For those who are interested in knowing more, there is a very good review papers by Tay and his college, just published a couple months ago. Right. So I have covers the classic models include feed-forward network, recurrent networks, convolution networks, and now the recent one, the transformer. So the question right now, one of the question right now that even though those guys are powerful, but is that enough for the world that we live in? The answer is probably not, because one thing that we didn't explicitly model and address was the arbitrary structure of the world, that neither irregulars or neither sequential or neither arranged the way that all of those models are assumed to run on. So that is the topic of the next part of the following part of the talks called graph neural networks.